Okay, let's unpack this. What if the space around you, the time ticking on your watch, aren't the stable realities we take them for?
Hmm.
What if they're more like a constantly shifting illusion shaped by something we don't even consciously perceive?
Right.
Today, we're plunging into the source of this mind-bending idea, Albert Einstein's relativity, the special and general theory, in his own words.
And what's fascinating here is that in 1916, Einstein took on this uh, really ambitious task, explaining these revolutionary concepts to a broad
Yeah,
audience.
not just physicists.
Exactly. People with a natural curiosity about science, philosophy, even if they weren't, steeped in advanced math.
Right.
His aim was genuine clarity,
Trying to make it accessible.
right, accessible to anyone with a solid education. And for those who wanted to go deeper, he thoughtfully included appendices, with the mathematical underpinnings.
That makes sense. So our mission today is to follow Einstein's lead. We're going to distill the core insights of special and general relativity. We'll focus on how he fundamentally challenged our ingrained notions of space, time, gravity, revealing a universe that's far more interconnected, more dynamic than our senses alone can grasp.
And if we connect this to the bigger picture, I mean, Einstein's work wasn't just a tweak to existing physics. It demanded a complete overhaul of our understanding of reality itself.
A total shift.
Yeah, he moved us from a universe seen as this, like, rigid clockwork mechanism with absolute space and time to one that's far more fluid, geometric even.
All right, so let's start right at the foundation, where Einstein discusses the physical meaning of geometrical propositions. We all likely remember Euclid from school, right?
Yeah, yeah.
Axioms, theorems. Geometry feels like the ultimate unshakable truth.
That's a great place to start, actually. Einstein emphasizes that within pure Euclidean geometry, truth, well, it really just signifies logical consistency within its own set of rules.
Internal coherence.
Exactly. It's about the system itself, not necessarily whether those perfect geometric forms directly mirror the messy reality we observe.
Right, it's a self-contained world of logic. But then comes the crucial step where Einstein connects this abstract world to the physical one.
Well, this is particularly insightful. When we add a physical idea to Euclidean geometry,
Yeah.
the proposition that the distance between 2 points on a, let's say, practically rigid object remains constant, regardless of how it moves.
Okay.
Suddenly, geometry isn't just math anymore. It becomes a branch of physics. Now, the truth of geometrical statements? Well, it's tested by experience.
Can we actually build these shapes? Do they behave as predicted?
Precisely. Can we construct them with real-world rigid materials and see them behave as predicted?
So, using a standard rigid rod, what Einstein calls S, to measure distance, transforms abstract geometry into something tangible, testable, part of our physical world.
And this leads to a vital point that Einstein comes back to later in his work, this idea of truth based on our everyday experience with rigid objects.
Yeah.
It turns out it has limitations, big ones, especially when we delve into general relativity and the warping of space itself.
Okay, fascinating. So, to navigate this physical space, we need a way to describe locations. That brings us to the system of coordinates. Seems straightforward, right? Like saying your house is at a specific address on Earth.
Precisely. Pinpointing an event's location always requires a rigid framework of reference.
Sure.
Earth serves that purpose for your address.
Our reference body.
Yes. And Einstein highlights that even extending this to 3 dimensions, using perpendicular x, y, and z coordinates, and measuring those with rigid rods, it all fundamentally relies on this concept of a rigid reference body. The physical meaning of those location specifications is entirely tied to this.
It's all relative, literally. Now, classical mechanics, the physics before Einstein, aimed to describe how things move in space over time. But Einstein immediately flags some potentially problematic terms: position and space.
Right. This raises an important question. What exactly do we mean by space in this context? Einstein uses a brilliant example. Imagine dropping a stone from a train moving at a constant speed. To someone on the train, it falls straight down. Simple. But to an observer standing on the ground, on the embankment, it follows a curved path, a parabola.
So what's the real path?
That's the crucial insight here. Motion isn't absolute. It depends on your perspective, your frame of reference.
And the answer is, neither path is inherently more real than the other.
Exactly. Einstein argues we should move away from this vague idea of absolute space and instead talk about motion relative to a practically rigid body of reference.
Got it. The path of the stone isn't an intrinsic property.
No, it's relative to the frame you choose, the train or the embankment. There's no independent, universally true trajectory.
And to fully describe motion, we also need time. Classical mechanics essentially assumed time was the same everywhere, right? That clocks could be perfectly synchronized without issue.
Yeah, they kind of took it for granted. But Einstein hints that there's a hidden complexity here that we'll definitely unpack later. He also mentions Galilei Newton's law of inertia.
The old object in motion stays in motion idea.
Pretty much. The idea that an object isolated from external forces will either stay put or keep moving at a constant velocity in a straight line.
Okay.
And what's significant about the law of inertia is that it implicitly defines special reference frames. We call them Galilean systems. These are frames where this law holds true in its simplest form.
Like the fixed stars.
Think of the distant fixed stars as a good approximation of bodies that obey inertia, yeah. But the Earth itself? Well, it isn't a perfect Galilean system because it's constantly revolving around the sun. It's accelerating.
Right. So these Galilean systems are essentially our baseline, our normal moving systems where Newton's laws work simply.
You got it. They're the non-accelerating frames.
Okay, so we have relative motion, these special Galilean frames. Now comes the principle of relativity,
Right.
at least in its restricted sense. What's the core idea here?
The restricted principle, yeah. It basically states that if you have two coordinate systems, one moving at a constant velocity in a straight line relative to the other, so no acceleration, no rotation.
Uniform motion.
Uniform motion, exactly. Then all natural phenomena will occur according to the same fundamental laws in both systems.
Like on the train again.
I imagine being inside that uniformly moving train again, yeah. If the windows were covered, you couldn't perform any physics experiment inside that would tell you whether you were moving or standing still. The laws are the same.
So the underlying rules of the universe don't care if you're moving at a constant speed.
That's the idea. And Einstein presents some quite persuasive arguments for this.
Such as?
Well, he points to the success of classical mechanics in accurately describing the movements of planets, stars, etc.
Celestial bodies.
Right. If the principle of relativity didn't hold, it'd be quite odd for these laws to work so well in mechanics, but maybe fail completely in, say, optics or electromagnetism.
Inconsistent.
Very. He also mentions the lack of any observed anisotropic properties of space on Earth. Despite our planet zooming through space, we don't see physical laws behaving differently depending on direction. North-south versus east-west, for example.
It all seems to work the same way no matter how we're oriented or moving. Okay. But now, this seemingly intuitive principle hits a major snag when we consider light.
Ah, yes, light. Here's where things get really counterintuitive.
I bet.
The established understanding, based on lots of experiments, was that light propagates through empty space at a constant speed.
Yeah.
We call it c, relative to a stationary, rigid reference body, like our familiar embankment.
Okay, constant speed c relative to the ground. But what happens if we consider that light traveling relative to our moving train?
Right, if we just add velocities in the classical way, the way Newton would.
It's like throwing a ball forward on the train.
Right.
Its speed relative to the ground is the train speed plus the ball speed relative to the train.
Exactly. So classically, the speed of light relative to the train should be c minus the train's velocity if the light is traveling in the same direction.
Makes sense, classically.
But here's the problem, and this is the crux of the issue. If the speed of light is different for observers in different uniformly moving frames, then the law describing light's propagation wouldn't be the same in all those frames, which directly contradicts the principle of relativity we just talked about.
Ah, so that's the clash, the core dilemma. A fundamental law seems to clash with a fundamental principle.
Precisely. You either dish relativity or you rethink light speed. And Lorentz's work in electromagnetism, well, it provided strong experimental support for the idea that the speed of light in a vacuum is constant, always c, regardless of the motion of the light source.
So experiments favored constant light speed. That put physicists in a tough spot.
A very difficult position, yes. Some were seriously considering discarding the principle of relativity.
But then Einstein steps in, and he offers a resolution by re-examining our most fundamental assumptions about time and space.
Starting with something that seems utterly straightforward, simultaneity.
Happening at the same time. Seems simple enough.
It does, doesn't it? But this raises a really important question. What does it truly mean for two events, maybe far apart, to occur at the same time? We think we intuitively understand this, but Einstein points out that for a physicist, a concept only becomes meaningful when we have a concrete way to determine if it holds true in a real-world scenario, a test.
So how does Einstein propose we define simultaneity in a physically meaningful way? How do we test it?
He introduces a definition based on light signals. Clever. Imagine 2 points, A and B, where events occur. Lightning strikes, maybe.
Okay.
If light signals are emitted from each event at the moment they happen, then those events are considered simultaneous if the light signals reach the midpoint between A and B at precisely the same instant.
Ah, measured at the halfway point.
Yes. But crucially, Einstein stresses that this definition of simultaneity is relative. It depends on the specific reference body we've chosen, like our embankment.
And this understanding of simultaneity directly leads to his definition of time at a particular location.
Right. Time at a specific point in space is simply what's read on a clock situated right there. Assuming, of course, that we can synchronize identical clocks placed at different points within our chosen frame of reference.
And is that assumption safe?
Well, that assumption itself, that identical clocks, once synchronized, will remain synchronized. That's a fundamental physical hypothesis within a given frame.
Okay. Now, equipped with this definition of simultaneity, Einstein unveils a truly mind-bending consequence: the relativity of simultaneity.
This is where our ingrained intuition about time really gets challenged. Let's go back to those lightning strikes. Happening simultaneously relative to the embankment.
Meaning the light flashes from both strikes reach the midpoint on the ground at the same time. Check.
Okay. Now, picture an observer on our uniformly moving train as it passes that midpoint, just as the flashes arrive there.
Right. The train is moving forward.
Because the train is in motion, the observer on the train will be moving towards the light signal coming from the front of the train, let's say from lightning strike B, and away from the light signal coming from the rear, say from strike A.
Ah, so the light from B has less distance to cover to reach the moving observer, and the light from A has more distance.
Exactly. As a result, the light signals will reach the observer on the train at different times.
Even though they hit the midpoint on the ground simultaneously.
Correct. The observer on the train will perceive the lightning strike at the front of the train, B, as happening earlier than the one at the back, A.
Wow.
Therefore, events that are simultaneous in one frame of reference, the embankment, are not necessarily simultaneous in another frame, the train, that's moving relative to the first.
So every reference body has its own particular time, its own definition of now.
That's the profound implication. Each reference body has its own unique concept of now. So now isn't universal. It's personal to your motion.
Wow. Wow. So this universal now that we all feel like we experience, it isn't so universal after all. It literally depends on how you're moving relative to the events.
Blew people's minds. Still does.
I can see why. Okay, next, Einstein tackles the relativity of the conception of distance. Time is relative. What about space?
Well, just like time, the measurement of distance also inherently requires a frame of reference. It's not absolute either.
How so?
Consider measuring the length of our moving train again. An observer on the train can simply use a measuring rod. Lay it down, measure end to end. Easy.
Right.
But how would an observer standing on the embankment measure the length of the moving train? Think about it.
They'd have to know where the front and back are at the same time.
Exactly. They would have to simultaneously, according to the definition of simultaneity on the embankment, mark the positions on the ground corresponding to the front and the back of the train. Then they measure the distance between those two marks on the ground.
Okay, that makes sense.
But here's the crucial point. There's no immediately obvious reason, no a priori reason, why these two measurements of the train's length, one taken by the observer on the train, the other by the observer on the embankment, should yield the same numerical value.
Because their simultaneity is different.
Precisely. This sets the stage for understanding why the classical ideas, those unjustifiable hypotheses of absolute time intervals and absolute space intervals, had to be discarded. They were the root cause of the apparent contradiction between constant light speed and relativity.
And by letting go of those assumptions, absolute time, absolute length, we can resolve the dilemma.
Yes, and we see why the classical way we thought velocities added together isn't quite right either.
Which brings us to the famous Lorentz transformation.
What's particularly insightful is that Einstein realized the need for a new set of mathematical equations, a transformation law.
To do what?
To relate the space and time coordinates of events as observed from two different uniformly moving frames like our embankment, K, and train, K1, in such a way that it guarantees the speed of light remains constant in both.
Ah, so it builds in the constant speed of light.
Exactly. The Lorentz transformation achieves precisely that. It replaces the old Galilei transformation.
And he contrasts this with the Galilei transformation, which was the set of equations used in classical mechanics.
Right, and he points out quite elegantly that the Galilei transformation is actually a special case. It's what you get from the Lorentz transformation if you pretend the speed of light is infinitely large.
Which is pretty good approximation for everyday speeds.
A very good approximation for cars and planes, yes.
Yeah.
But not for light itself or things moving close to that speed. And Einstein mathematically demonstrates that if a light signal travels at speed uc in frame kx east rule ct, the Lorentz transformation ensures that it will also be measured to travel at speed c in the moving frame k1 by 1 ct1. It works.
Okay, so the math holds up. But what are some of the truly mind-bending implications of this Lorentz transformation? It leads to some very counterintuitive behaviors for measuring rods and clocks.
Oh, yes. This is where we encounter length contraction and time dilation. And they are weird.
Length contraction first.
Length contraction means that an object, say a meter rod, moving in the direction of its length with the velocity v, will appear shorter to a stationary observer.
Shorter. How much shorter?
The amount it's shortened is determined by a factor, the square root of 1v squared over c squared.
So involving its speed relative to the speed of light.
Exactly. The faster it moves, the shorter it appears in that direction.
Mhm.
And as v approaches c, the length approaches 0. It implies c is an ultimate speed limit.
You can't reach it because the length would become 0, or...
Well, the energy required also goes to infinity, as we'll see. Yes, length contraction comes extreme. Now, what about time dilation?
Time slows down.
In a sense, yes. Time dilation describes how a moving clock runs slower than an identical clock that is stationary, relative to the stationary observer.
By the same factor.
By that exact same factor, SCORT 1v2c2. The time interval between two ticks of the moving clock, as measured by the stationary observer, is longer than the interval between ticks of their own stationary clock.
So if I watch your clock fly past me very fast, I see its seconds ticking by more slowly than my own seconds.
That's precisely it. Again, c represents an unattainable limit. Things moving faster experience time slower relative to a stationary observer. Just let that sink in. Rulers shrink, time itself slows down, depending on motion.
It's almost unbelievable. Space and time themselves are stretching and shrinking depending on relative velocity.
And Einstein emphasizes this is perfectly consistent with the principle of relativity. It has to be reciprocal.
Meaning?
Meaning, someone on the moving train, K1, looking back at the meter rod stationary on the embankment, K, would also see it as shortened by the same factor. And they'd see the embankment clock running slow. It's symmetrical.
Okay, that's crucial for consistency. Now, building on this, Einstein revisits adding velocities. Classical mechanics had that simple, intuitive rule. How does relativity change that?
Well, the relativistic formula for adding velocities, which you can derive from the Lorentz transformation, is different from the classical one, u plus v. It's more complex.
And the crucial insight here is?
The crucial insight is that this new formula ensures that you can never combine velocities in such a way that the resulting velocity exceeds the speed of light c. C remains the cosmic speed limit no matter what.
So you can't just keep adding speeds indefinitely.
Nope. The formula prevents it mathematically. Einstein even mentions Fizeau's experiment measuring the speed of light in moving water as experimental evidence that supports these relativistic ideas about velocity addition, not the classical ones.
Right. This brings us to the heuristic value of the theory of relativity. What does Einstein mean by a heuristic here, a tool?
Exactly. He means that the theory acts as a powerful tool for discovery, a guide. By uniting the principle of relativity and the constant speed of light, we arrive at the Lorentz transformation.
The new rules for space and time.
Yes. And this then leads to a fundamental guiding principle. Every general law of nature, any fundamental law, must maintain the same mathematical form. It must be covariant under Lorentz transformations.
Meaning the equation looks the same regardless of which uniformly moving frame you're using.
That's it. If someone proposes a new fundamental law of physics, and it changes its form when you apply a Lorentz transformation, well, that suggests the proposed law is wrong or incomplete. Or maybe relativity itself is wrong, but the evidence points to relativity being right in its domain.
So it serves as a filter, a test for potential laws of physics.
A very powerful one. Now, what are some of the broad consequences that have emerged from special relativity? Big picture stuff.
Einstein explains that special relativity originated from studying electricity, magnetism, and light electrodynamics and optics. And it actually led to a more unified, simpler theoretical structure for these fields.
Fewer assumptions needed.
Right, reducing the number of independent hypotheses. It also revealed that classical mechanics, Newton's laws, need modification for really high speeds, speeds approaching c.
Which is particularly relevant for things like electrons, ions, subatomic particles.
Exactly. And this modification leads to the famous relativistic formula for kinetic energy, how things gain energy when they move.
And a key implication of this formula is that as an object's velocity gets closer and closer to c, its kinetic energy doesn't just increase linearly, it increases dramatically, approaching infinity.
Ah, so that's another reason c is a speed limit. It would take infinite energy to reach it.
Correct. It reinforces c as an ultimate speed limit in the universe.
Yeah.
And then, of course, there's the profoundly important concept of mass-energy equivalence.
EMCPSE, probably the most famous equation ever. How does Einstein explain this relationship in the book? Does he just state it?
No, he actually derives it. Conceptually, at least.
Yeah.
He describes a thought experiment involving a body moving, and it absorbs some radiation, some energy in the form of light.
Okay.
By applying the principles of relativity, conservation of energy, conservation of momentum, he demonstrates that as the body absorbs energy, its mass must also increase.
Energy has mass.
Or rather, mass is a form of energy, and energy has a mass equivalent. The increase in mass is directly proportional to the energy absorbed, divided by c squared. This leads to the understanding that even the energy a body has when it's just sitting still, its rest energy, is given by mc paths.
So the profound implication here is the interchangeability of mass and energy. They're two sides of the same coin.
Fundamentally, yes. This has enormous consequences, suggesting mass and energy are just different manifestations of the same basic stuff. And it also leads to the rejection of instantaneous action at a distance.
Like Newton's gravity acting instantly across space.
Right. Relativity implies that interactions forces information. They can't propagate faster than light, so interactions happen at a finite speed, the speed of light.
Okay. Now, it's natural to wonder, how well does special relativity hold up against reality? What's the evidence?
Well, Einstein points out that it's supported by all the experimental evidence that validates Maxwell-Lorentz electromagnetism, because special relativity grew out of it and made it consistent.
Okay, so a huge body of evidence there.
A huge body. It also accurately predicts phenomena like the aberration of starlight, that apparent shift in star positions due to Earth's motion, and the Doppler shift of light from distant stars moving towards or away from us.
Things astronomers observe routinely.
Exactly. Furthermore, it provides a consistent explanation for the behavior of fast-moving particles like cathode rays, electrons, and beta rays, also electrons or positrons from radioactive decay, without needing extra kind of ad hoc assumptions about the internal structure or shape of electrons that older theories needed.
It cleans things up, theoretically.
It does, and crucially, it also offers a natural and elegant explanation for that puzzling negative result of the Michelson-Morley experiment.
The one looking for the ether, the medium for light waves.
That's the one. It famously failed to detect this hypothetical ether wind as Earth moved through it. Special relativity just eliminates the need for the ether altogether. Light doesn't need a medium in the way relativity frames it.
So it explains the null result naturally.
Naturally. And it also explains the Lorentz-Fitzgerald contraction, that shortening of moving objects we talked about, not as some weird physical squashing caused by moving through the ether, but as a fundamental property of how space and time are measured between moving frames. It just falls out of the theory.
Wow. Okay, so special relativity seems really solid experimentally within its domain. It paints a picture of a universe far stranger and more interconnected than we typically imagine.
Definitely. And then Hermann Minkowski comes along and provides an even more abstract yet powerful way to conceptualize it: four-dimensional space-time.
Space and time woven together.
What Minkowski realized was that by treating time not as something separate, but as a fourth dimension mathematically on a similar footing to the three spatial dimensions, x, y, z,
It simplified the math.
it made the mathematical framework of special relativity significantly more elegant, more unified, and it offered deeper insights. Each event in the universe, something happening at a specific place in a specific time, can be thought of as a single point in this unified four-dimensional world, or continuum, described by four coordinates, x, y, z, and t.
So instead of thinking about objects moving through space as time progresses,
We have this single unified fabric, this continuum of space-time. Events are just points in this fabric, world points.
why hadn't physicists traditionally viewed the world this way? It seems neat.
Because in classical physics, time was considered absolute, universal, entirely independent of space and the observer. It flowed the same for everyone, everywhere.
But relativity showed that's not true.
It's exactly. Minkowski demonstrated that within the framework of relativity, space and time are inextricably linked. They're perceived differently, they mix, depending on the observer's relative motion. He even discovered a formal mathematical connection between this four-dimensional space-time and familiar three-dimensional Euclidean space by using an imaginary time coordinate. He makes the math look very symmetric.
Sounds complex, but he said it enhanced clarity.
It did. For physicists working with the theory, it provided a powerful geometric language for relativity.
Okay, so that's special relativity, uniform motion, no gravity involved really. But Einstein knew that wasn't the whole story.
Gravity was the big missing piece.
So he takes the next monumental step with the general principle of relativity. He revisits the special principle, the relativity of uniform motion, but he felt limiting relativity only to these special, non-accelerating Galilean frames was fundamentally incomplete, unsatisfying.
This raises a crucial question, a philosophical one almost. Why should some reference frames, those moving at a constant velocity, be considered special or privileged over others, like those that are accelerating or rotating?
Like a spinning carousel or a car hitting the brakes.
Exactly. Einstein uses a wonderful analogy. Imagine two seemingly identical pots on a stove, one boiling vigorously, the other perfectly still. We would instinctively look for a physical reason for this difference, right?
Sure, one's got the heat on high.
Right. Similarly, he argued, we should strive for a theory of physics where all frames of reference, all observers, regardless of their motion, are treated equally. The laws of physics should look the same for everyone.
That sounds incredibly ambitious.
It was. This leads to the general principle of relativity. All frames of reference, regardless of their state of motion, uniform, accelerating, rotating, whatever, are fundamentally equivalent for the description of natural phenomena and for formulating the general laws of nature.
The law should be universal, truly universal.
Precisely. Einstein was deeply influenced by Ernst Mayr's critique of Newtonian mechanics, which highlighted this very issue of privileged inertial frames. The general principle aims to create a physics where the laws maintain their form no matter how you, the observer, are moving.
And this incredibly radical idea has some profound consequences, particularly for understanding gravity.
Oh, absolutely. What's particularly insightful is that the general principle provides a theoretical pathway to understanding the properties of the gravitational field. It connects gravity and acceleration.
How? Through the equivalence principle.
Essentially, yes.
Yeah.
He revisited his earlier thought experiment of the accelerating chest or elevator. Remember, if you were in a closed box accelerating upwards in empty space...
You feel pushed down like gravity.
Exactly. Indistinguishable locally from gravity.
Mm.
Conversely, someone freely falling in a gravitational field feels weightless, just like someone floating in a Galilean frame far from any gravity. This suggested a deep link between acceleration and gravity.
Okay, but the truly novel and crucial result is what this implies for the path of light, right?
Yes, this was a huge prediction. In a Galilean frame, free from gravity, light travels in a straight line at constant speed c locally. We know that from special relativity.
Right.
But Einstein realized that within an accelerating frame, and therefore due to the equivalence principle, within a gravitational field, the path of light is no longer straight. It must curve.
Light bends due to gravity.
Yes.
Hmm.
Think about light crossing that accelerating elevator. From inside, its path looks curved downwards. So gravity must bend light. This had two immensely important implications.
Okay, what were they?
First, it presented a prediction that could actually be tested. Through observation, Einstein calculated that starlight passing very close to the sun, where gravity is strong, would be bent by a tiny but measurable angle. About 1.7 seconds of arc, he figured.
Tiny angle. How could you even see that?
You'd need a total solar eclipse. When the sun's glare is blocked, you can photograph the stars near the sun's edge. Then compare their positions to photos taken when the sun isn't there. The stars should appear slightly shifted outwards due to the light bending around the sun.
And did they test it?
They did. Famously, Sir Arthur Eddington led expeditions during the 1919 solar eclipse.
Hmm.
And the results? Well, they confirmed Einstein's prediction. It was huge news, compelling early evidence for general relativity.
Wow. What was the second implication?
The second profound implication is that the principle of the constant speed of light in a vacuum, that cornerstone of special relativity, is only strictly valid locally, or in the complete absence of a gravitational field. In the presence of gravity, the speed of light can vary depending on the gravitational potential, though it's still the local speed limit.
So gravity affects light's speed too, not just its path.
In a sense, yes. As measured over distances by observers in different gravitational potentials, it's all tied to the geometry of space-time being curved.
Okay, so how does general relativity actually solve the problem of gravitation? What is gravity in this picture?
It's a radical rethinking. Einstein starts by considering a region of space-time that's flat, Galilean no gravity. Then, by mathematically transforming to a non-Galilean accelerating frame of reference, a gravitational field effectively appears. It's induced by the change in coordinates.
Like the feeling in the accelerating elevator.
Exactly. The way measuring rods, clocks, and freely moving particles behave in this transformed frame reveals how gravity, or acceleration, influences them. Rods might measure differently, clocks tick at different rates.
Time dilation and length contraction again, but now linked to gravity acceleration.
In a way, yes. The goal then is to generalize this understanding, to find a fundamental law for the gravitational field itself, a law describing the curvature of spacetime that holds true regardless of the specific choice of reference frame, independent of the observer's motion. What Einstein picturesquely called describing physics within a mollusk, a reference frame that could be arbitrarily twisting and deforming.
The equations of gravity itself, describing the shape of spacetime.
Correct. And this generalized law needs to be consistent. It must reduce back to the laws of special relativity in regions where gravity is negligible, flat spacetime. And it should approximate Newton's law of gravity for weak fields and slow speeds.
So what are the major triumphs of this new theory of gravitation? Did it work?
Oh, it worked beautifully. Beyond its intrinsic mathematical elegance and finally getting rid of those problematic privileged reference frames.
What did it explain?
Well, first, it provided a natural explanation for that long-observed, mysterious equality of inertial mass, resistance to acceleration, and gravitational mass, how strongly something gravitates. In GR, they're fundamentally the same thing because gravity is the curvature caused by mass energy, and objects follow the straightest possible path, a geodesic, through that curved spacetime.
Okay, that's big. What else?
It also beautifully and accurately explained a persistent astronomical anomaly, the anomalous perihelion precession of Mercury.
Its orbit wobbles slightly more than Newton predicted.
Exactly. A tiny extra wobble, about 43 seconds of arc per century, that couldn't be fully accounted for by the gravitational pulls of other planets using Newtonian mechanics. General relativity predicted this extra wobble with remarkable precision, right out of the equations.
Wow, explaining a known problem. That's powerful validation.
Very powerful. And of course, it shows that Newton's theory of gravity is an excellent first approximation for weak fields and low velocities, which is why it works so well for most everyday situations and planetary orbits, besides Mercury's subtle deviation.
And the other predictions.
The predictions of the bending of light by gravity, confirmed during those solar eclipses, and also the gravitational redshift of spectral lines. Light, losing energy and shifting to lower frequencies as it climbs out of a gravitational field, have also been repeatedly confirmed observationally.
Okay, so general relativity seems incredibly successful. Now, shifting focus slightly, Einstein also talks about cosmological challenges, problems when applying Newton's theory to the whole universe.
Yes. He mentions Hermann von Seeliger's point. If the universe is infinite in extent and stars are distributed roughly uniformly throughout it, well, Newton's law of gravity, an inverse square law, leads to a very perplexing conclusion.
Which is it?
Infinite gravitational forces everywhere, which is physically nonsensical. It doesn't work on the largest scales.
So Newton's theory implies the universe can't be infinite and uniform.
Not easily. Newton's theory tended to suggest maybe a finite island universe, a clump of stars surrounded by infinite empty space. But Einstein found that picture unsatisfactory too.
Why?
Because light and stars would just escape into this infinite void forever. There'd be no overall structure or interaction on the largest scale. It felt incomplete, unstable.
This leads to the intriguing possibility he discusses.
A universe that is finite and yet unbounded. How can something be both limited and have no edges? That sounds like a contradiction.
It does, if you're stuck thinking only in terms of flat Euclidean geometry. But non-Euclidean geometries, developed by mathematicians like Riemann, showed that space doesn't have to be flat and infinite, like the surface of the Earth.
That's the classic analogy. Consider two-dimensional beings living only on the surface of a sphere. Their universe, the sphere's surface, is finite in area.
Yes, definitely finite.
Yet, it has no boundaries, no edges. They could travel forever in any direction and never fall off. They just keep going around.
And they could even figure out their space is curved.
They could, by doing geometry. For example, if they drew a very large circle and measured its circumference and diameter, they'd find the circumference is less than pi times the diameter, unlike in flat space. That tells them their world is curved, positively curved, like a sphere.
Okay, that makes sense for 2D. Is there a three-dimensional equivalent?
Yes, that's Riemann's concept of spherical space, a 3D hypersphere. It possesses a finite total volume, but it has no boundaries. and all points within it are equivalent. There's no center.
So if you traveled in a straight line,
If you traveled in what feels like a straight line, a geodesic, in this spherical 3D space, you would eventually end up back where you started, coming from the opposite direction.
whoa, like in some video games.
A bit like that, yes. He also mentions elliptical space as another possibility, which is related but slightly different topologically. The key idea is that geometry allows for finite, unbounded spaces, and general relativity provides the theoretical tools to explore whether our own universe might be finite in this way, potentially resolving those cosmological difficulties of Newton's theory.
So according to general relativity, what actually determines the structure of our space? Is it flat? Is it curved? Finite? Infinite?
General relativity makes a profound statement here. The geometrical properties of space, its curvature, are not fixed and absolute. They are determined by the distribution of matter and energy within it. Mass tells space-time how to curve.
Matter shapes geometry.
Exactly. As a rough approximation, Einstein notes that stars and galaxies move relatively slowly compared to light speed. So for a large-scale picture, we can consider matter as being roughly at rest, on average.
Okay, simplifies things.
Now, if you assume the universe has some average density of matter, which it clearly does, general relativity predicts that a perfectly uniform distribution of this matter is incompatible with an infinite, flat, Euclidean universe. That solution doesn't work with gravity.
Why not?
The calculations based on general relativity suggest that a universe with a uniformly distributed average density of matter would naturally curve back on itself. It would be spherical, or possibly elliptical, positively curved, and therefore finite in volume, though still unbounded.
So the presence of matter itself makes the universe finite.
According to the simplest cosmological models based on GR, yes. Our real universe, of course, isn't perfectly uniform. Matter is clumped into galaxies, clusters, voids. So the actual geometry would be quasi-spherical, meaning it's locally very close to flat, which agrees with our local observations. But on the very largest scales, it possesses an overall positive curvature and is therefore necessarily finite.
Mind blown again.
And the theory even provides a mathematical relationship. It connects the overall size of the universe, its radius of curvature, r, and the average density of matter, usually represented by the Greek letter rho. More matter means stronger curvature, potentially a smaller, finite universe.
It's a complete revolution in our understanding of the cosmos. Moving from that static, infinite, clockwork universe of classical physics to this dynamic, interconnected, potentially finite and matter-determined space-time of general relativity.
A radical shift.
So just to recap some of the biggest takeaways from this deep dive into Einstein's own explanations. We've learned space and time aren't absolute. They're relative to motion. They stretch and shrink.
Relativity of simultaneity, length contraction, time dilation. Yeah.
The speed of light in a vacuum is a fundamental constant, a cosmic speed limit for observers in uniform motion, at least locally.
Built into special relativity via the Lorentz transformation.
Gravity isn't some mysterious force pulling things across empty space. It's the curvature, the warping of space-time itself, caused by the presence of mass and energy.
Objects just follow the straightest paths, geodesics, through this curved geometry.
Mass and energy are fundamentally equivalent. EMC/FTR. Two sides of the same coin.
With staggering implications.
And the universe itself on the grandest scale might not be infinite, but finite and yet unbounded. Its very shape dictated by the matter within it.
A self-contained, curved, finite cosmos.
What's truly remarkable looking back is how these seemingly abstract ideas completely challenge our most deeply ingrained everyday intuitions about reality.
They really do. But by carefully following Einstein's logical progression, his thought experiments, his reasoning, we gain this profound, entirely new perspective on the cosmos. You get those incredible aha moments about the true interconnectedness of space, time, matter, energy, geometry.
It all fits together in this incredible new way.
It does.
So here's a final thought for you, listening, to ponder. If our perception of something as seemingly fundamental as space and time can be so relative, so dependent on motion and gravity, so utterly mind-bending, what other aspects of our reality, which we currently take for granted as fixed and absolute, might actually be far more fluid, more interconnected than we currently realize?
That's a deep question.
Think about the profound implications of a universe that might actually be finite. Consider the inseparable link between matter and the very fabric of space-time. Perhaps this deep dive has ignited a new spark of curiosity.
Hopefully encouraging you to delve even further into the ever-evolving, truly fascinating fields of cosmology and modern physics. There's still so much to explore.